After 40,000 years under the faint light of an unknown star, a piece of ancient metal floats in the cold, dark expanse of interstellar space. This is Voyager 1, which was sent by human civilization in 1977. Suddenly, an unknown civilization has spotted this spacecraft. Their eyes fall on a shiny, gold-plated golden record which contains the sounds, music, and many pictures of Earth. They touch it, and in that very moment, the voices of human civilization from millions of years ago echo before them. But will they be able to understand it? And will this message truly be able to tell our story? This scene leads us to a question. In 1977, when Voyager 1 and Voyager 2 bid farewell to our solar system with the golden record, they carried a time capsule of our world with them. But today, if we launch Voyager 3, would we send such a golden record again? Or will the technology of our digital age help us do something else, something more complex, something bolder? How will we tell our story to those distant civilizations in the endless darkness of interstellar space, and will there really be anyone out there to listen to our story? In 1977, when Voyager 1 and Voyager 2 left Earth, they were not just machines. They were messengers of humanity. They were sent to explore the outer planets of the solar system: Jupiter, Saturn, Uranus, and Neptune. A rare planetary alignment provided an opportunity to hop from one planet to another using gravity assist. Voyager 1 visited Saturn's moon Titan, and then it left the solar system and moved out into interstellar space. But Voyager 2 traveled all the way to Uranus and Neptune, and then it too set out on an endless journey beyond the solar system. But the real strength of these spacecraft is not in their discoveries, but in what they carried with them. There was a message, the golden record. This idea belonged to Carl Sagan and his wife Anne. It was a phonograph record made of copper plated with gold, and it came with a stylus. It was meant to be played at 16 and 2/3 revolutions per minute, not the usual 33 revolutions per minute, so that as much data as possible could be stored on it. This record was much more advanced than the ordinary metal plaques of Pioneer 10 and 11, which were launched in 1972 and 1973. On the Pioneer spacecraft, only the name of the spacecraft and the original location of our Earth were written, but the golden record was a complete story in itself, of Earth, of our humanity, and of our hopes. It was placed in an aluminum cover, which had a layer of uranium-238 on it. Uranium was used for two reasons. It is 5 times more effective than lead at blocking cosmic rays and X-rays, and its decay can help you determine the age of a record from an unknown civilization. The golden record was not just a scientific experiment, it was a bold step. It was risky. Should we share our information with unknown civilizations? Some believed that it could be dangerous, but science is progressing so slowly, at about 56,000 to 71,000 kilometers per hour, that it would take them 77,000 to 84,000 years just to reach our nearest star, Proxima Centauri. It would take so long that is beyond our imagination. 20,000 years ago, humans lived in the Stone Age. Now, during the digital revolution, how much has technology advanced? If we survive for another 20,000 years, maybe we will have become a spacefaring civilization ourselves. But the question remains the same. If we send Voyager 3 today, will we send something like the golden record again? Or will our technology show us a different way? Will our message still be that simple? Or would we want to throw something more complex into the cosmic ocean? The golden records of Voyager 1 and Voyager 2 are among the most daring attempts of human civilization, even though we have sent them off with complete protection. But will these records really last for eternity, or will the cruel forces of the cosmic ocean silence them forever? As far as interstellar space is concerned, it's definitely not empty at all. It's a place where there's interstellar dust with particles even smaller than a micrometer. They collide with Voyager at speeds of about 50,000 to 70,000 kilometers per hour. Each collision creates a tiny crater, which can slowly damage the surface of these spacecraft and possibly even the golden records. These particles are so small that their size is about 1,000th of a millimeter, but their speed makes them deadly. In addition, there are charged particles from the solar wind and super cosmic rays coming from NUA or black holes can knock atoms out of the crystalline structure of the golden record. Over millions and billions of years, these processes can weaken the record. National Aeronautics and Space Administration had already understood this danger. That's why the golden record has been placed in an aluminum cover which has a coating of uranium-238 on it. This will protect it from the harsh environment of interstellar space. An infographic has also been made on this cover which explains how to actually play the record. But the question is, how will an unknown civilization, which might be using completely different technology, actually understand this? The golden record is based on 1970s technology, analog pictures and sounds with 512 vertical lines. It was once a marvel, but now seems outdated. Scientists like Nico Bug at the Captain Astronomical Institute have calculated how the different paths of the Voyager spacecraft will affect their golden records. The Voyager 2 is heading towards a red dwarf star called RAS 248, which is about 17 light years away, and it will take more than 30,000 years to reach there. However, it will encounter less interstellar dust. But Voyager 1, which will pass through a denser dust cloud in the galaxy, its cover might wear out more and faster. This will also increase the risk of damage to the record. But still, scientists estimate that these records could last for about 5 billion years. But by then, the Milky Way and Andromeda galaxies will have collided. What will happen to the Voyagers in this collision? OBA's models suggest that there is a 20% chance that the Voyagers will be thrown out of the new galaxy during this time. The Golden Record dared to carry the story of humanity into interstellar space in the 1970s. It was a phonographic record made with the most reliable technology of that time. But today, we are living in an era of digital revolution. If we launch Voyager 3, will we rely on such analog technology again? Or will our modern technology show us a path that is more powerful, more complex, and more risky? In today's world, data storage means terabytes, petabytes, and nanoscale technology. Fused quartz disks, which are written with femtosecond lasers, could be a revolutionary option for Voyager 3. In quartz disks, we can store entire books, videos, scientific data, and perhaps even a summary of the entire internet. But this is where a mysterious challenge arises. In fused quartz disks, data is written at the nanometer scale in 2 optical dimensions and 3 spatial dimensions. To read that data, a technique is required that perhaps only an advanced civilization might possess. The Golden Record's simplicity was their strength. Anyone could play it with a stylus and some instructions, but reading the quartz disk would require laser technology and nanoscale decoding. Are we ready to take the risk that some unknown civilization might not be able to understand our complex technology? There's another question. If we send an electronic reader with Voyager 3, will it be able to withstand the harsh conditions of interstellar space? Cosmic rays, interstellar dust, and charged particles can destroy any electronic devices over millions of years. Even if fused quartz disks last for 14 billion years, the equipment to read them might become useless in just a few thousand years. zone. Then our message, no matter how detailed it is, will be lost in silence forever. The strength of the golden records was their simplicity. They were like a vinyl record that anyone could understand without complex technology. But today, our digital world gives us the opportunity to send more data, more stories, and more complex messages will remain. The golden records of Voyager 1 and Voyager 2 dared to send the story of human civilization into interstellar space. This was an attempt filled with hope and curiosity. But if we launch Voyager 3 today, would we dare to send a similar message again? But this time, the question is even bigger. Should we reveal our existence to the universe? Some people had warned us while making the golden records. Should we give our information to unknown civilizations like our location, our culture, and our weaknesses? Could a hostile alien civilization misuse this information? But today, this question has become even more serious. Voyager is much slower compared to the speed of light. It will take more than 20,000 years just to cross the outer shell of our solar system, that is the boundary of the Oort cloud. This means that if any civilization finds these probes within our lifetime, then maybe they are already present in our solar system. But this risk isn't just from hostile aliens. If we send a new message with Voyager 3, like fused quartz disks, which can store 307 terabytes of data. So what would happen if it somehow fell into the wrong hands? Today, in our digital world, data brokers, targeted ads and tracking have made our personal data a business. Our emails, names, addresses, ages and professions are sold just to exploit us. If this is a security threat even on our own planet, then how dangerous could it be to send the entire story of our human civilization into interstellar space? This is just as deep an ethical question. Do we have the right to decide whether the story of our civilization should be sent into the universe? If we send our entire digital history with Voyager 3, our wars, our mistakes, our achievements, if we send all this, are we unknowingly exposing our weaknesses? Or is it our responsibility to leave our voice in the cosmic ocean, to show that we existed, we dreamed, and we tried? Will Voyager 3's message be our hope, or will it become our greatest mistake? Voyager 1 and 2 sent golden records as time capsules, which could reach an unknown civilization millions or perhaps billions of years from now. But if we launch Voyager 3 today, would we choose such simplicity again, or would we opt for the powerful technology of the digital age? Imagine billions of years from now, when the Milky Way and Andromeda galaxies collide, these Voyagers, or at least their golden records, might still be floating in this cosmic ocean. Interstellar dust and cosmic rays might have worn them down, but they would still be protected by uranium-238. Those records would be wandering somewhere, preserving the last traces of human civilization, waiting for someone in case some civilization finds them. Then they will hear our laughter, our lives, our music, and our dreams. They will know that a small planet, a tiny blue dot, once wanted to reach the stars. But what will Voyager 3's message be? As Carl Sagan said, our message should be very simple so that every civilization can understand our story. Or maybe we'll rely on techniques like nanoscale. Knowing that maybe only the most advanced civilization will be able to read it, are we willing to take the risk that our location and our weaknesses might reach a dangerous civilization? This is a question that forces us to think about how to define our place in the universe. This story is not just about the Voyagers, it's our story. It's the story of that curiosity which gave us the courage to look beyond the Oort cloud towards stars like Ross 248 and maybe even into intergalactic space. Launched in 1977, National Aeronautics and Space Administration's Voyager 1 and Voyager 2 spacecraft have embarked on an extraordinary journey for our human civilization. Today, as they travel through this infinite universe, they have gone farther than any other man-made object. The first Voyager mission was designed for only a 5-year mission period to explore Jupiter and Saturn. But the Voyagers performed far better than the scientists had expected. It completed all its missions on time and then was sent on to further missions. It was sent again on a never-ending journey to this infinite darkness-filled universe. And today, Voyager 1 is about 14 billion miles away from our Earth, and Voyager 2 isn't far behind either. And it is continuously traveling through this infinite dark-filled universe. But the question is, how did National Aeronautics and Space Administration manage to keep these spacecraft operational for so long, despite such great distances and harsh space conditions? To keep them alive, you also needed cleverness, skill, talent, and some luck. Carefully managing power, continuously providing accurate software updates, and overcoming technical challenges. The Voyager mission team has made every possible effort to keep these spacecraft's historic journey going. In today's video, we will explore the strategies and techniques that National Aeronautics and Space Administration has used to keep these Voyager spacecraft operational for more than 4 decades. What kind of challenges did these distant explorers have to face? How did the mission team implement clever solutions? And what challenges lie ahead for these spacecraft as they continue their journey into interstellar space? At every turn of this story, an unsolved mystery is hidden. Will these Voyagers be able to succeed in revealing even more distant mysteries of this universe to us? After all, how long will National Aeronautics and Space Administration be able to keep these spacecraft alive? The journey of Voyager 1 and Voyager 2 is not only a milestone for space exploration, but this mission also teaches us how, even with limited resources and extreme conditions, innovation and determination can make the impossible possible. RTGs, radioisotope thermoelectric generators, are a key reason the Voyager spacecraft have stayed operational so long. They provide the power. Radioisotope thermoelectric generators, or RTGs, are different from our traditional solar panels that depend on sunlight. But they can't be used in deep space? That's why RTGs were used in the Voyager spacecraft. RTGs. They convert the heat generated from the natural decay of radioactive material into electricity. For Voyager, the radioactive material used is plutonium-238. RTGs have provided the Voyager spacecraft with a continuous and reliable power supply, which has allowed Voyager to remain operational in deep space. This technology is especially ideal for those missions where sunlight is limited, or where there is no sunlight at all. For instance, in outer planets and interstellar space, plutonium-238's natural decay produces heat, which thermoelectric materials convert directly into electricity. This process happens without any moving parts, which makes RTGs extremely reliable and long-lasting. However, over time, plutonium-238 decays, which gradually reduces the power output. But even so, the Voyager spacecrafts have far exceeded their expected lifespan. This is a result of the durability of the mission's design and engineering. How do RTGs work? RTGs are a type of nuclear battery that convert the heat produced by the decay of radioactive isotopes into electricity. Each Voyager spacecraft has 3 RTGs, which contain plutonium-238 oxide. When plutonium decays, it releases heat, which is continuously converted into electricity through thermocouples. Thermocouples are devices that generate voltage when there is a temperature difference. In 1977, when the Voyagers were launched, their RTGs were generating about 470 watts of electrical power. But as plutonium decayed over time, the heat and consequently the electrical power produced by the RTGs gradually decreased. Today, the RTGs produce about 40% less power than originally, generating just 250 watts. But despite this, the Voyager spacecrafts have managed their power very efficiently. The mission team shut down non-essential systems immediately after their use was over, and the instruments have been very carefully prioritized so that they continue to collect scientific data even with limited power. And that's the reason why Voyager 1 and Voyager 2 are still sending us valuable information from interstellar space even today. The long-lasting capability of RTGs has made the Voyager mission an incredible example of how, with advanced technology and smart engineering, we can maintain our existence in deep space for a long time. For power management to keep the Voyagers operational with decreasing power supply, National Aeronautics and Space Administration also carefully managed the spacecraft's power consumption. Over the years, the mission team has systematically turned off non-essential instruments and systems to conserve power. This approach has made it possible to keep critical systems like the communication system and some key scientific instruments operational. For example, the Voyager team has turned off the heaters of those instruments that are no longer in use, and also such non-essential systems like tape recorders, which used to store data before transmitting it. This careful power management has allowed the Voyagers to continue their mission despite the continuously decreasing energy reserves. Heat and thermal management is another big challenge with RTGs. Managing the heat generated from decaying plutonium. Just like on Earth, excess heat can become a problem even in the cold vacuum of space. The visors are designed with a thermal control system that uses louvers for heat rejection and insulation to retain heat within the system. And this entire system regulates the spacecraft's internal temperature. This whole thermal management system keeps the instruments and electronics within their operational temperature range. As the power output of the RTGs decreases over time, the heat generated by them is also decreasing. Because of this, it is becoming difficult to keep the spacecraft systems warm. The Voyager team has to maintain a perfect balance between the spacecraft's power and thermal management so that its critical components don't fail due to excessive cold temperatures. In addition, the Voyager team has also used innovative methods like adjusting the spacecraft's orientation so that the instrument can also be kept a little warm from the sun's heat. All of this is like a complex dance where every decision affects the spacecraft's survival and scientific output. Despite all these challenges, Voyager 1 and Voyager 2 have continued their incredible journey to this day. Software updates and problem solving from billions of miles away. Keeping the Voyager spacecraft operational was not just possible by managing power, but maintaining the health of their systems and software is just as important. In the past years, the Voyager mission team has troubleshooted many problems. Voyager was also sent several critical software updates and many creative solutions were devised, that too from billions of miles away. The most remarkable thing about the Voyager mission software updates is that these spacecrafts have received software updates despite such vast distances. In the beginning, the spacecrafts had only 69 kilobytes of memory, which is very little compared to today's standards. To maximize the use of this limited memory, the Voyager team designed the software to be highly efficient. After the mission goals kept evolving, the team had to make several software updates so that new tasks could be performed or bugs could be fixed. These updates were sent from Earth via radio signals, which take about 20 hours to reach the spacecraft. For example, when Voyager 1 was given the task of taking the famous pale blue dot image in 1990, the mission team had to specially reprogram the spacecraft so it could aim its camera at Earth to diagnose and solve problems remotely. As the Voyagers moved farther away from Earth, the communication delay kept increasing, which made real-time problem solving more and more difficult. The team has to send commands to diagnose problems based only on the data received from the spacecraft. It can take them several hours or even days to see the results. One incident happened in 2010 when Voyager 2 started transmitting confusing data. After analysis, the mission team identified that one bit in the computer memory had flipped from 0 to 1, which was causing a malfunction in the data processing system. By sending a series of commands, the system was reset again, and after that the spacecraft returned to its normal operation. This was a huge achievement, especially at that time when this spacecraft was about 9 billion miles away from us. Dealing with aging hardware was tough. The spacecraft is now over 45 years old and its systems have far exceeded their expected lifespan. Aging is evident in components like thrusters, gyroscopes, and communication systems, so the mission team must find creative solutions. For example, the spacecraft's thrusters, which adjust its orientation, have been working for 4 decades. Because the thrusters have become inefficient, they require more power, which is often used to perform maneuvers. To conserve power, the mission team reprogrammed the spacecraft so that the thrusters are used less frequently and there is more reliance on the reaction wheels. At another point, when the mission team discovered that Voyager 1's primary communication antenna was going off target due to changes in the spacecraft's orientation, to solve this problem, the mission team developed a new strategy to keep the antenna pointing correctly using a combination of thrusters and reaction wheels. Innovative problem solving in the Voyager mission. The team had to get creative to solve the problem of the spacecraft's aging systems. In some cases, the team even developed completely new techniques to minimize hardware failures or limitations so that the antenna keeps pointing towards Earth and communication remains possible. In 2019, when Voyager 2's power levels suddenly started to drop, several of its instruments had to be shut down. The mission team identified that due to the sudden voltage drop, the spacecraft had triggered a power protection mode. To prevent this problem, the team reprogrammed the spacecraft so that critical systems could be prioritized and the instruments would remain operational under all circumstances, no matter how much the power levels fluctuated. Overcoming communication challenges is one of the biggest challenges for the Voyager mission team. Maintaining continuous communication with Voyager, especially at such vast distances as the Voyagers move farther from Earth, the travel time for signals keeps increasing and the strength of their signals is continuously weakening. Because of this, communication is becoming increasingly difficult. To communicate with the Voyager spacecrafts, National Aeronautics and Space Administration primarily uses its Deep Space Network or Deep Space Network. It's a global system of large radio antennas located in California, Spain, and Australia. The Deep Space Network is a critical component of the Voyager system, providing a link between Earth and distant spacecrafts. As the Voyagers traveled farther from Earth, the Deep Space Network upgraded its equipment to maintain constant communication. For example, in 2012, National Aeronautics and Space Administration upgraded the Deep Space Network antennas with new receivers. These had higher sensitivity, making them capable of detecting even the faint signals from Voyager 1 and Voyager 2. The Deep Space Network antennas were also improved, increasing their sensitivity. Signal delay and data transmission are unique challenges when communicating with the Voyagers, and that is the significant time delay involved in exchanging signals. Currently, it takes about 21 hours for a signal to travel from Earth to Voyager 1 and another 21 hours for the response to come back. This round-trip delay is about 2 days. This makes real-time communication almost impossible, and that's why the mission team has to carefully plan and sequence their commands. To maximize the efficiency of data, the Voyagers use a technique called data rate reduction. In this technique, scientific data is compressed before being transmitted, allowing the spacecraft to send more data in a short amount of time. The Deep Space Network then decompresses and processes this data on Earth, ensuring that no valuable information is lost. Precise antenna pointing and tracking are necessary to maintain a stable communication link with the Voyagers. As the spacecraft is continuously traveling in space, we have to constantly change the orientation of our antennas to keep receiving signals from there. Because of this, the Deep Space Network has to constantly adjust the position of its antennas as well. The Voyager mission team has developed sophisticated algorithms for this, which precisely predict the spacecraft's trajectory and orientation. These algorithms take into account the gravitational influence of planets and celestial bodies, as well as the spacecraft's own movement, and they ensure that the antennas remain accurately locked on their target. In 2020, the Deep Space Network made a major upgrade to improve its capabilities, in which National Aeronautics and Space Administration added a new 34-meter antenna in Madrid, Spain. This upgrade further enhanced the capabilities of the Deep Space Network so that it can easily communicate with distant spacecrafts like Voyagers and ensure that they remain in contact with Earth for as long as possible. Future of Voyager missions. Now, as the Voyager spacecrafts continue their journey into interstellar space, eventually one day their power levels will drop below the minimum threshold required to operate instruments or communicate with Earth. National Aeronautics and Space Administration estimates that after 2025, the RTGs will not have enough power left to keep the spacecraft systems operational. And when this happens, the Voyagers will fall silent and their historic mission, which was providing us with valuable data, will come to an end. But even after the power runs out, the spacecrafts will continue to wander through this infinite space with their golden record, which is a message from our human civilization to those future aliens, a testimony of our existence for those intelligent aliens who might someday be able to reach these spacecrafts. The journey of the Voyagers represents humanity's first step into interstellar space, which is beyond the boundaries of our solar system. They have expanded our understanding about the outer planets, about our solar system, and have revealed many mysteries of the heliosphere. This mission also gave us valuable data on the Kuiper Belt and interstellar medium. Their legacy will continue to inspire our future scientists, engineers, and explorers. Conclusion. Looking towards future space exploration, the Voyagers remind us that when we push the boundaries of our knowledge and capabilities, nothing is impossible. Their remarkable journey demonstrates the power of human curiosity and ingenuity, and their story is not over yet. Even after falling silent, the Voyagers will continue their journey through the cosmos, carrying our message to the stars. Friends, what are your thoughts on this? Be sure to let us know in the comment section. If you like this video, be sure to like it and share it with your friends.